Introduction to Aromaticity. Aromaticity is one of the most fundamental concepts in organic chemistry, explaining why certain cyclic molecules possess superstability that defies standard expectations for alkenes. This unique behavior isn't just a curiosity, it dictates how these molecules react, their physical properties, and why they serve as the structural backbone for everything from DNA bases to synthetic dyes. To truly understand aromaticity, we must look beyond simple Lewis structures and examine the behavior of electrons within a closed loop of p orbitals. The core concept: stability through delocalization. In a typical alkene, pi electrons are stuck between two specific carbon atoms. In an aromatic system, these electrons are delocalized, meaning they are shared equally across the entire ring. This creates a pi cloud above and below the plane of the molecule, significantly lowering the overall energy and making the molecule far less reactive toward addition reactions that would break this stable loop. Rules of aromaticity. Aromatic compounds exhibit exceptional stability due to delocalized pi electrons across a cyclic, conjugated system. This lowers the overall energy compared to localized bonds. This delocalization arises from resonance involving p orbitals perpendicular to the molecular plane, stabilizing the molecule beyond what simple cyclic conjugation would. To qualify as aromatic, a molecule must satisfy all four criteria. 1. Cyclic, the structure must contain a ring, allowing continuous overlap of p orbitals around the cycle. Acyclic molecules, or open chains, cannot achieve this loop. 2. Planar, the ring must be flat, ensuring all p orbitals align parallel for optimal overlap. Non-planar rings, such as boat-shaped structures, disrupt this alignment. 3. Fully conjugated, every atom in the ring must have a p orbital, either sp2 or sp hybridized, enabling resonance delocalization. sp3 atoms with tetrahedral geometry lack a p orbital, breaking conjugation. 4. Hückel's rule. The pi system must have for n plus 2 electrons, where n is a non-negative integer, 0, 1, 2. This empirical rule from molecular orbital theory ensures a filled, stable set of molecular orbitals. As shown in the flowchart, check structural rules first. Electron count is irrelevant if any fail. Skipping this is a common error. Remember, planarity and full conjugation are interdependent. True conjugation forces planarity due to p orbital alignment needs. Determining aromatic compounds. Let's continue applying our rules to finalize the classification for the remaining structures. We will focus on the interplay between structural requirements and Hückel's electron counting rules. Case 1, the 12-annuline system, structure 1. Looking at our first example, we find a large cyclic hydrocarbon. Structural check, the molecule is cyclic, and as we observe, every atom is sp2 hybridized, meaning there are no obstacles to full conjugation. The electron count, we have 6 pi bonds. Counting 2 electrons per bond, we have a total of 12 pi electrons. The verdict, feeding 12 into the for n plus 2 formula results in a non-integer, n equals 2.5. However, 12 fits the for n rule perfectly where n equals 3. Because it is cyclic, fully conjugated, and follows the for n rule, this molecule is anti-aromatic. Example 2. Let's dive into example number 2. At first glance, this large ring looks complex, but we can break it down using the same fundamental principles. Case 2, the alkyne ring. First, the basics. The molecule is obviously cyclic. And while large rings like this can sometimes twist in 3D space, for this exercise, we are assuming planarity. We imagine this molecule as perfectly flat. The hybridization check. Looking at the atoms, most of the ring consists of sp2 hybridized carbons. However, we have a triple bond in the middle, which means those two atoms are sp hybridized. sp hybridization does not block conjugation. In fact, it provides p orbitals just like sp2 does. So, the molecule is fully conjugated. The triple bond trick. Now, counting the electrons is where it gets tricky. In a triple bond, we have 2 pi bonds. Imagine one pi bond sitting vertically in the same plane as the rest of the ring's p orbitals. This one is part of the conjugation. The second pi bond, however, sits perpendicular at 90 degrees to that plane. The count. Because the second pi bond is orthogonal to the system, those electrons cannot see the rest of the aromatic circuit. From the triple bond, we count only 2 electrons. Adding the electrons from the 5 double bonds, 5 times 2 is equal to 10, we reach a total of 12 pi electrons. 12 electrons do not fit the 4n+2 rule. Instead, 12 follows the 4n rule, n equals 3. Classification, since it is cyclic, planar, and fully conjugated but has a 4n electron count, this molecule is anti-aromatic. The takeaway here? When you see a triple bond in a potentially aromatic ring, ignore the extra pi bond. Only one of them can join the party. Example 3. The acyclic illusion, structure 3. At first glance, this molecule might look like a cyclic compound simply because of how it's drawn on the paper. It sits in a circular arrangement that mimics a ring. The reality check: if we look carefully at the structure, we see that there is no bond between the oxygen and the carbon at the bottom right. The first rule, our very first criterion for aromaticity is the molecule cyclic? The verdict: because there is no connection, this is an acyclic or open-chain molecule. It doesn't matter how many electrons it has or if the atoms are sp2 hybridized, if the loop isn't closed, the electrons cannot delocalize in a cycle. Classification, since it violates the very first rule of aromaticity, this compound is non-aromatic. And there you have it. Always start with the structure, check the conjugation, and only then, if the racetrack is clear, count the electrons. Example 3. Let's continue our step-by-step breakdown using our fundamental rules. Remember, for this exercise, we assume planarity for all structures unless otherwise specified. Case 4, the sp3 interrupt, Phenanthrene-like system. Take a close look at structure number 4. The logic: while the molecule is cyclic, we run into a major problem with conjugation. The problem: one carbon atom at the top of the ring is sp3 hybridized. For full cyclic conjugation, every single atom in the ring must be at least sp2 hybridized to provide a p orbital. The verdict: this sp3 carbon acts as a hard stop. Resonance can occur through the sp2 part of the molecule, but it cannot complete the full cycle. Since it fails the conjugation rule, this molecule is non-aromatic. Example 5. Now, let's analyze structure number 5, where a hidden structural feature changes everything. Case 5, the sp3 interrupt, Phenanthrene-like heterocycle. In this molecule, we see an oxygen atom with lone pairs. It's tempting to start counting those electrons immediately for a Hückel calculation. But we must pause and check our structural rules first. The structural analysis: we observe a ring that is cyclic, yes. However, we immediately identify a critical flaw: there is a carbon atom that is sp3 hybridized. The hard stop: for full cyclic conjugation to occur, every single atom in the ring must be sp2 hybridized to provide a continuous loop of p orbitals. The verdict: because that sp3 carbon lacks a p orbital, it acts as a hard stop. While resonance can happen locally in the sp2 section of the molecule, it cannot complete the circuit. Classification: since the conjugation is interrupted and the loop is broken, this molecule is non-aromatic. No electron counting is necessary when the structure itself cannot support delocalization. Remember, you can have all the right electron counts in the world, but if the racetrack has a wall in it, the electrons can't run the lap. Always look for that sp3 hard stop before moving to the math. Example 6. Now we arrive at structure number 6, a molecule called Phenanthrene. It looks big and scary, like a complex honeycomb, but our rules will make short work of it. Case 6, Phenanthrene, the fused system. First, we look at the shape. The logic: it is obviously cyclic. While it is composed of 3 fused rings, it forms one continuous framework. The hybridization check: looking at every single carbon atom in this structure, we see they are all sp2 hybridized. Conjugation, because every atom has a p orbital, we can draw a full, uninterrupted cycle of resonance throughout the entire three-ring system. There are no hard stops here. The count. Now, we count the pi electrons. We have 7 pi bonds total across the 3 rings. 7 times 2 is equal to 14 electrons. The verdict. Now we apply Hückel's rule, for n plus 2 is equal to 14. Solving for n, we get n equals 3. Since 3 is a whole number, this molecule satisfies the electron count requirement for stability. Classification, cyclic, fully conjugated, and having 14 electrons makes this molecule aromatic. Phenanthrene proves that no matter how many rings you fuse together, if the p orbitals form a continuous loop and the electron count fits for n plus 2, you have an aromatic system. Example 7. Thiophene, the sulfur heterocycle, our 5-membered sulfur ring. The logic, sulfur has 2 lone pairs. Since it has no existing pi bond, it donates 1 pair to a p orbital to complete the circuit. The count, 2 pi bonds, for electrons, plus 1 lone pair, 2 electrons, equals 6 pi electrons. The verdict, 6 satisfies for n plus 2, n equals 1. Result, aromatic. Example 8 now, let's look at a smaller, more unique case. Case 8, the cyclopropanyl cation. This 3-membered ring is the smallest possible cyclic system we can evaluate. The logic, it is obviously a cyclic molecule. While small, it contains 2 atoms from a pi bond and a carbocation. Conjugation check, carbocations are sp2 hybridized species. This provides an empty p orbital, meaning there are no obstacles to full cyclic conjugation. We can use this carbocation in resonance. The count, we have 2 electrons from the pi bond and exactly 0 electrons sitting on the carbocation. The verdict, if we apply Hückel's rule, for n plus 2 is equal to 2, we get n equals 0. Since 0 is a valid whole number for this formula, the electron count is correct for stability. Result, this molecule is aromatic. Example 9. We are nearing the end of our challenge. Let's look at our last structure, starting with a molecule that is more a theoretical warning than a stable reality. Case 9, Cyclobutadiene. This molecule is a cyclic, 4-carbon system. The logic, it is obviously cyclic, and every carbon atom is sp2 hybridized, providing no obstacles to conjugation. The count, it contains 2 pi bonds, totaling 4 pi electrons. The verdict, because it is cyclic and conjugated but fits the 4n rule, n equals 1, instead of for n plus 2, it is anti-aromatic. Fun fact, this is the smallest anti-aromatic molecule possible. It is so unstable that it essentially does not exist in a free form. It is largely a theoretical example of extreme electronic instability.